Hello, everyone. This program transcribes what I say. For it to work, I have to speak very clearly. Let's see how it works.
Hey there. In this video series, I'm going to be talking about my latest project, which is a speech recognition project. What speech recognition is, just to give a simple definition, is essentially the automated transcription of an audio file. So we have our source data are short clips of people speaking, and our target data is the words that were actually said by that person. These videos are going to be following pretty closely in format to some of my previous videos on AI. So what I mean by that is we're going to be doing kind of like an end-to-end look. So coming from like our source data, how the data is actually processed, and how the processed data is used to train the model, and then how the model predictions are used to give the best kind of final results possible. So I hope you guys enjoy. Okay, so this project uses the library speech dataset as its the dataset to be used to train the model. So just to give a quick overview, this is just the dataset that I downloaded. It's freely available on the internet, and this is the format that mine came in. So we can drill down into these folders. I think that these are sorted by speaker. And this is what your final audio file looks like. So we have this transcription file, a text file, which gives the sort of ID of the file, and then we have a little, generally these clips are
Northanger Abbey
are probably between 2 and like 15 seconds. There's a little bit of range in them. But yeah, they are FLAC files sampled at 16K hertz. There's a little bit of a process that we do. We don't take just the raw file. So I want to show that here. I think if I run this function, so this is basically, this is our GenDB files function. This is how I'm sort of taking that raw data and doing some processing. This is sort of just stuff that I don't want to be doing at runtime when we're training the model, because I think some of it's computationally expensive, so it just made sense to kind of run that at the start and then use that as kind of another data set. I don't want to really get into this stuff. There's no need for this video to be crazy long like some of my other ones. So let's just skip to this block where it kind of gets interesting. This is all just navigating to those files and kind of like associating the right transcription with the right audio file. So what we have first here, there is a library called SoundFile that we're using. This is just what reads the FLAC file and turns it into a format that we can work with. So if I step through here, we now have data, which is this array that's really, really long. It's sampled at 16 kilohertz, so each of those readings, and I think it's just an audio wave, so kind of the amplitude at that moment. So what we're going to be doing here, this is the kind of data processing that I was talking about. We're going to be changing the raw audio file to the MFCC coefficients, or sorry, MFCC version of the audio file. So basically what that means, and I'm not an expert on what on the actual process of MFCC transformation, but it's my understanding is that it's first off we choose an amount of channels, and it kind of works like a spectrogram. So it's for certain windows within the audio file, it's finding the frequencies that are most pronounced. That's how a vanilla spectrogram works. MFCs are more nuanced. They use like a log scale instead of just like linear frequency bands. There's a little more to it than that, but the idea is like it's supposed to kind of like emulate more useful information for how human hearing actually works, at least as far as language goes. So you'll see these come up again and again in like these sorts of like speech recognition domains. For the amount of base channels, I have a couple project variables that are held in here, but well, 3. Um, so this is how many output channels that we get. And basically what so 13 channels is kind of seen as like all that's necessary, at least in English. I think that value is actually different between languages, but in English 13 channels is actually okay. And then we're also going to be taking the derivatives of that data. So first off, let's get our t data value. We step again, and our t data is down here, so we can see we have an array of 13, and it's gotten much shorter. There is we have the hop length and the window length. So we're looking at a window of 25 milliseconds, and it hops 10 milliseconds for each sample. So that's how we went from, can't really tell the number off the top of my head, 225,000 down to 1409, 1409 steps on those 13 channels. Then here we're just going to be taking the derivative. So we have from NumPy import diff. We're going to be taking the derivative of the data and also the second derivative. And with that, we are ready to dump it, and this is going to be the data that's used later to train our model. So we can do that. And then here, I'm going to introduce the concept of phonemes. So there's basically multiple ways that speech recognition can be done. We can try and output the text, so the letters. Some models actually can be used to output phonemes. So what a phoneme is, that's actually a good time to go back to here. We can see for one-hot encoding, we have our alphabet here. So this is for the letter version of the model, so A is encoded to 1, B is encoded to 2, etc., all the way through the alphabet. And we also have the apostrophe and a space character. Those are our target outputs. For the phonemes, it's quite a bit longer, but basically these are the components of English language, acoustically. So all of these sort of like vowel sounds and consonant sounds. So every English sound can be made up of these. So we can So a syllable, for example, is a combination of a maximum of 3 phonemes. You can have your starting consonant, which is optional, your vowel, which is necessary, and your ending consonant, which is optional as well. Hopefully that explanation made sense. What we're doing here is we're kind of just taking the verbal sentence. So we can look at that. I think that I have words here. Yeah. So we can look at our words variable, and this is the sentence that we're transcribing here to the phoneme version. And for each word here, so we are using this. This is from the NLTK library, so Natural Language Toolkit. This is basically just like a dictionary that converts words to their phoneme equivalents. So we have word. So our word here is chapter. And now we have sounds. So this is what the output looks like. We have chapter. And then it also gives kind of an emphasis, or this integer value like indicates whether the accent is on that syllable, I think. I actually got rid of those. We're about to strip those sounds. And then here, eventually, like not every word is in this dictionary, so that's why this block kind of looks messy. Basically, I didn't get I didn't get too detailed, too hung up on the details here. I just said like, oh, if the word's not in the dictionary, then just whatever, we'll disregard that sentence. So the phoneme data set is about, I think, like 2/3 the size of the letter data set. That's pretty much all I want to show in this function, I think. In the case where it's successfully, where there's no problems, we just dump our sequence of phonemes into a slightly different file, and we use both of those when we're training a phoneme model. The other useful function here is just a test train split. Nothing too interesting here, but the process data is all going into one folder. And then here we have our split ratio, and we're just sorting them into a train and an eval folder. Yes, that's pretty much all that goes on here.